Beyond the Martian sky, something transcended the stars in October of 2025, as the Perseverance rover's night vision cameras registered a striking 60 km per second light, mirroring the speed and timing of Interstellar Visitor 3, or I-Atlas, during its historic transit past Mars. Martian satellites scheduled for observation mysteriously ceased transmitting, and their raw image feeds dissolved into an unnerving silence. Subsequently, unverified accounts of multiple swift-moving entities and an enigmatic green luminescence cast the scientific community into a state of heightened anticipation. Initial photographic evidence from the Mars flyby suggested something atypical. Its behavior defied the characteristics of any known comet, and official data releases experienced an inexplicable delay precisely when crucial answers were most needed. What transpired during those missing visual sequences? And could these veiled clues fundamentally alter our understanding of visitors from beyond our solar system? On the second day of October 2025, Stephen Burns, a prominent figure within the amateur astronomical community, uploaded a 9-minute time-lapse sequence of the night sky, sourced from Perseverance's raw image repository. This compilation, meticulously assembled from a series of contiguous frames, showcased a solitary, incredibly fine streak traversing the Martian celestial backdrop. Its apparent velocity, measuring 60 kilometers per second, immediately stood out, vastly exceeding the speeds of any meteor, satellite, or cosmic ray artifact typically detected in Mars rover data. For comparative context, NASA's Parker Solar Probe, the fastest human-made conveyance, attains speeds of 192 kilometers per second, and this only occurs at its closest approach to the Sun, within the Sun's intense gravitational pull. Here, the streak maintained a consistent pace at Mars's orbital distance, a speed typically associated with celestial wanderers from other star systems. Burns's analytical approach was painstakingly thorough. He meticulously aligned the raw frames with a catalog of fixed stars, calibrated the image scale using known stellar separations, and verified the temporal accuracy of each timestamp. The streak's movement was quantified relative to the background stars on a frame-by-frame basis, effectively ruling out any fixed camera aberration or isolated cosmic ray impact. After resolving frame dropouts and cross-referencing with public celestial charts, he disseminated the complete composite image and extended an invitation to the broader scientific community to either corroborate his findings or refute them. The outcome was a widespread phenomenon. Tens of thousands of individuals downloaded the image frames, reprocessed the stacking procedures, and engaged in fervent discussions about the streak's authenticity, its potential as an artifact, or the possibility of something far more extraordinary. Burns's established reputation for meticulous technical accuracy and inherent skepticism lent considerable weight to his disclosure. He was swift to emphasize the imperative for independent verification, urging others to refrain from premature, extraordinary conclusions until the streak's origin had been independently validated. The computation was unequivocal. If the measured 60 kilometers per second proved accurate, the trajectory aligned almost perfectly with the predicted celestial motion of 3I Atlas. However, the onus of proof now shifted outwards. The amateur astronomical community embraced this challenge. Could anyone else reproduce the anomaly, or would it simply dissolve under closer examination? Online forums ignited with activity as soon as Burns's time-lapse video became publicly accessible. Within mere hours, hundreds of independent analysts downloaded the Perseverance frames, eager to either replicate or debunk the 60 kilometer per second streak. The ensuing debate quickly fractured. Some reported successful reanalysis, employing custom scripting to stack the image frames. They asserted that they had detected not only the primary track, but also indications of secondary fast-moving objects within the October 3rd data. Conversely, others utilizing alternative processing methods found only discernible noise. Accusations of excessive data fitting and artifact hunting were exchanged vigorously. At precisely 3 minutes past midnight, UTC, a brief flash of green light appeared within one group's animated sequence. This anomaly, detected at the pixel level, triggered a cascade of speculative theories. Was it an actual energetic emission event, or merely the magnified impact of a cosmic ray amplified by aggressive stacking techniques? Rival analytical teams meticulously dissected the color channels, debating the merits of calibration procedures and filter settings. Some maintained that the green flash exhibited chemical plausibility consistent with a cometary emission line. Detractors, however, countered that Mars's tenuous atmosphere and the quirks of the camera's sensor made such ephemeral flashes more likely to be digital illusions rather than tangible phenomena. The absence of unprocessed, raw imagery only amplified the prevailing uncertainty. Without direct access to original FITS files and camera telemetry, every assertion remained provisional. Statistical analyses designed to evaluate signal-to-noise ratios, frame-to-frame consistency, and cosmic ray rejection became contentious battlegrounds. The lack of official data dissemination, the absence of any swift pipeline output, and the withholding of calibration scripts fueled pervasive suspicion. Was this simply the customary inertia associated with tracking moving celestial bodies, or an indication of something more deliberately concealed? The collective frustration within the community intensified. Some advocates called for institutional arbitration, imploring NASA or ESA to intervene and definitively resolve the technical disputes. Others doubled down on their commitment to open-source analysis, publishing their code and intermediate image stacks in the hope of achieving crowdsourced validation. The very reality of the detected signal remained suspended, its ultimate fate now inextricably linked to whether the forthcoming Mars orbiter observation campaigns would yield conclusive, independently verifiable imagery. For a brief period in early October, Mars served as the solar system's premier observation post for an interstellar visitor. 3 orbiters, the Mars Reconnaissance Orbiter, MRO, equipped with its high-resolution imaging science experiment, HiRISE camera, the European Space Agency's Trace Gas Orbiter, TGO, carrying its color and carbon suite for aerial spectroscopy, CASIS instrument, and Mars Express with its high-resolution stereo camera, HRSC, were all tasked with observing the object as it passed at a distance of 3 to 9 million kilometers. This vast gulf, approximately 75 times the distance between Earth and the Moon, was so immense that even Mars's most sophisticated camera, HiRISE, would likely perceive the object as little more than an indistinct blur. Its optimal resolution capability extended to dozens of kilometers per pixel. HiRISE, designed specifically to discern boulders on Martian slopes, had never before been directed at a target moving with such velocity or at such extreme distances. Its imaging protocols were reconfigured for the flyby, utilizing updated ephemeris data to precisely aim its narrow field of view ahead of the object's predicted trajectory. Each exposure represented a calculated risk. Aiming too early meant the object would depart the frame. Aiming too late risked it vanishing against the backdrop of stars. CASIS, engineered for color imaging and the analysis of gaseous jets, was prepared to capture a series of 4-band exposures, with the intention of detecting not only the central nucleus, but also any potential fragments or trailing jets. Mars Express's HRSC, with its expansive coverage and multiband capabilities, was assigned the task of surveying for any gross structural features. Could it differentiate a singular nucleus from a collection of debris, or discern a sunward jet against the overwhelming glare? This observational campaign necessitated meticulous coordination. Each orbiter's observation plan was contingent upon precise predictions generated by JPL's Horizon system, which were updated daily as the trajectory of 3I Atlas was continually refined. The spacecraft themselves had to deviate from their standard pointing directions, sometimes by several degrees, to track a faint, moving speck against the vastness of space. Onboard limitations precluded any form of real-time tracking. Each captured image was essentially a snapshot, reliant on the accuracy of last-minute trajectory calculations. For objects situated at interplanetary distances, even a minor deviation in the ephemeris could result in a complete observational miss. As the flyby approached, the instrument teams juggled numerous competing priorities, maximizing exposure durations, minimizing cosmic ray interference, and allocating precious bandwidth for rapid data transmission. Every single frame was destined for intense scrutiny, in search of even the slightest hint of structure. Was 3I Atlas a singular, solid entity, a loosely aggregated collection of fragments, or something altogether more perplexing? At this considerable range, only features spanning tens of kilometers could potentially be resolved. The capture of multi-band color data, if successful, might offer insights into its chemical composition, with broad green, blue, or red streaks potentially indicating exotic materials. The stakes involved were exceptionally high. With terrestrial telescopes rendered ineffective by solar interference, the Mars orbiters represented the sole unimpeded observational window. The prevailing expectation was straightforward. Should any unusual phenomena occur, such as fragmentation, the ejection of jets, or the presence of companion objects, these images would be the primary source of evidence. The entire mission was a race against geometric constraints, celestial motion, and the relentless passage of time. The phrase, "no raw images," resonated through every ongoing discussion as the days following the Mars flyby continued to tick by. Typically, Mars orbiter data, particularly from high-profile events, becomes accessible in public archives within a few days of its transmission to Earth, at least in its uncalibrated form. This time, however, there was a complete absence of data. Nothing was forthcoming from HiRISE, nothing from Cassis, and not even the standard preliminary quick-look frames from Mars Express were released. The silence was absolute, punctuated only by the occasional TUR, telemetry uplink request, status updates, which vaguely alluded to ongoing calibration and quality assurance procedures. Within the Jet Propulsion Laboratory, JPL, the imaging teams faced a different kind of pressure. The challenge transcended mere bandwidth limitations or administrative delays. It encompassed the inherent risk of disseminating image frames contaminated with cosmic ray impacts, uncorrected malfunctioning pixels, or misaligned stacked images that could be erroneously interpreted as genuine fragments or jets. For a rapidly moving celestial target like 3I Atlas streaking across the sky at 60 kilometers per second, conventional processing pipelines proved inadequate. Standard procedures such as flat fielding, geometric correction, and radiometric calibration all required substantial reworking. Even the most sophisticated cosmic ray rejection filters, typically optimized for the slow-moving Martian surface, struggled to distinguish between a genuine interstellar streak and the spurious trace of a stray charged particle. The lead imaging scientist at JPL, speaking under the intense weight of public scrutiny, characterized the entire process as a race against both inevitable errors and heightened expectations. Each individual frame demanded meticulous verification for any registration drift. Did the predicted ephemeris data accurately align with the observed celestial motion? Could a cosmic ray or a solar particle have produced a transient streak that might be misinterpreted as a companion object? For this particular observational campaign, even the routine act of stacking multiple images transformed into a complex minefield. A fractional misalignment could exponentially amplify artifacts. Conversely, an overly aggressive stacking process risked obscuring faint, genuine features. The implications were stark. Premature release of data could ignite a global frenzy fueled by digital misinterpretations, while an excessive delay would only intensify accusations of a deliberate cover-up. The calibration team painstakingly processed each frame, cross-referencing the predicted trajectory of the target with the actual pixel trails and flagging any anomalies for manual review. Every potential fragment, every unusual flash, was meticulously logged, subjected to rigorous debate, and either cleared or escalated for further investigation. No one at JPL expressed any satisfaction with the prolonged delay. The reality was a bottleneck of extreme caution, a deliberate prioritization of scientific integrity over expediency. Even as the world anxiously awaited, the forthcoming data release would be tasked with answering more than just public curiosity. It would need to provide definitive evidence, settling the critical question of whether Mars's cameras had captured a singular nucleus, a cluster of fragments, or something that necessitated an entirely new explanatory framework. The characteristic green luminescence of a comet, observed from millions of kilometers away, typically presents a straightforward diagnostic scenario. Dicarbon, or C2, emits a distinct bright green signature when exposed to sunlight, which causes its molecular bonds to break. This process is so reliably predictable that comet hunters utilize it as a definitive chemical identifier. However, in the case of through Atlas, the narrative becomes considerably more complex. Reports emanating from the Mars flyby observation period claimed the detection of a fleeting green flash at precisely 03 UTC within some of the processed Perseverance image stacks. The implication is straightforward. If this flash is indeed genuine, it would indicate the presence and active state of dicarbon within the comet's coma. Yet, early preliminary spectral analyses conducted by Mars Express and TGO suggest the opposite. The anticipated C2 emission bands are either notably weak or entirely absent, replaced by a volatile mixture rich in carbon dioxide and notably deficient in classic carbon chains. From a laboratory perspective, a green flash devoid of dicarbon presents a stark contradiction. Standard cometary physics offers no simple explanation for a spectral signature that glows green, yet lacks the characteristic swan bands observed at 516 and 563 nanometers. If the observed color is authentic, it necessitates the existence of a novel emission mechanism or the presence of an unexpected contaminant. Spectroscopists, trained meticulously to identify and dismiss false positives, urge a cautious approach. Without calibrated, time-synchronized spectral data directly correlated with the precise moment of the reported flash, the chemical paradox remains unsubstantiated. Was the green luminescence a genuine energetic emission, or merely a digital artifact arising from the complexities of image stacking and color correction? Until the raw data from the Mars orbiters is publicly released, the only means of resolving this perplexing contradiction lies in obtaining direct, instrument-verified spectral readings. Spectral data acquired during the Mars observation campaign arrives as a direct challenge to established cometary science textbooks. Early reports from the Mars Express team highlight an emission signature predominantly characterized by nickel rather than iron, a reversal of the typical spectral profile observed in comets within our solar system. Nickel emission lines, usually faint or entirely masked by iron signatures, now dominate the observed spectrum. Planetary chemists meticulously examining these abundance ratios note that no existing standard formation models predict such an inverted order of elemental prevalence. The anomaly does not cease with metallic elements. Instruments aboard the trace gas orbiter reveal a volatile composition where the outgassing of carbon dioxide significantly exceeds that of water vapor by an order of magnitude. For a comet experiencing increased solar heating, water vapor is expected to be the dominant volatile. Here, carbon dioxide reigns supreme, with water appearing in negligible quantities. The geometry of the observed jet further complicates the picture. Images captured by the Mars orbiters, even at their limited resolution, depict a plume not trailing away from the Sun, as is typically observed, but rather blasting directly forward. This phenomenon, described as an anti-tail, is sunward directed and remarkably sharply defined. The trajectory of this jet descends so abruptly that dust dynamics models struggle to accurately replicate its behavior. The conventional, broad, fan-shaped tail is conspicuously absent. Instead, the leading edge of the plume exhibits a crisp definition, with an unnaturally steep brightness gradient. Teams employing dynamic simulations estimate that only an exceptionally large and dense nucleus could sustain such a directed plume without succumbing to rotational forces or being significantly deflected from its course. Tracking teams meticulously calculate the object's mass by monitoring for any non-gravitational acceleration, subtle deviations in its trajectory caused by jetting activity or uneven outgassing. For 3I Atlas, the results are starkly silent. Despite observable activity, its orbital path adheres almost perfectly to the predicted gravitational arc. This implies a lower bound of 10 billion tons, suggesting it is far more akin to an asteroid than a typical comet. Each observed anomaly is diligently logged, intensely debated, and integrated into a progressively expanding body of evidence. Naturalistic models are being stretched to their limits in an attempt to explain the observed chemistry, the complex dynamics, and the sheer estimated mass. The stakes continue to escalate as the scientific community grapples with the question of whether these peculiar signatures indicate an object that simply redefines the established rules of cometary behavior, or something that cannot be readily dismissed as a purely natural phenomenon. Avi Loeb, renowned for his pioneering research in interstellar studies, enters the discourse with a provocative computational analysis. His research team conducted orbital simulations, meticulously tracing the path of 3I Atlas backward over several decades to ascertain if its trajectory might have intersected with the location of the famed 1977 WOW signal, a 72-second radio burst detected at 1,420 megahertz, the hydrogen spectral line. Employing JPL's Horizon system and Monte Carlo simulations, they estimated the probability of such a coincidental alignment in the sky to be approximately 0.6%. While this is a statistically rare occurrence, it is not entirely outside the realm of possibility. The hydrogen line frequency holds particular significance within SETI, Search for Extraterrestrial Intelligence, circles, as it represents the most probable frequency for interstellar communication. Loeb's group contends that if any celestial object warrants a dedicated radio follow-up investigation, it would be one that traverses the coordinates associated with the WOW signal and exhibits interstellar velocity. SETI researchers, ever cautious, highlight the inherent limitations, including positional uncertainties, the immense vastness of space, and the inherent risk of post hoc reasoning. Nevertheless, the specific narrow-band nature of a hydrogen line signal remains the universally accepted benchmark for identifying artificial origins. Natural phenomena do not typically broadcast with such focused spectral precision. With 3I Atlas now having passed behind the Sun, entering a period of observational blackout, the lingering question remains: will the next available radio window reveal anything beyond silence? Following October 29th, 3I Atlas slipped behind the Sun, entering a zone of invisibility that effectively blinds observers both on Earth and on Mars. For the subsequent 5 weeks, no telescope will be able to track its position, luminosity, or evolving physical structure. This period of obscured observation is not unusual. Its closest approach to the Sun, known as perihelion, invariably necessitates a forced pause dictated by the intense solar glare and stringent safety protocols for spacecraft. Throughout November, planetary scientists, amateur astronomers, and proponents of technosignature detection will meticulously monitor the calendar, anticipating the object's reappearance in the pre-dawn sky in early December. Four critical metrics will dominate the observational watch list: its overall brightness, its trajectory relative to background stars, the morphology of any observable tail or jets, and its spectral characteristics. Each of these elements will be subjected to rigorous scrutiny for any discernible changes. Has the object fragmented further, diminished in brightness, or altered its course? The upcoming observational window, though brief, promises to be decisive. The ultimate verification will hinge upon what emerges from behind the solar shadow and whether the incoming data aligns with existing predictions or further deepens the existing enigma. The process of discerning a genuine signal from mere noise commences with a fundamental hierarchical approach. At the foundational level lies repeatability. Authentic features, whether they manifest as streaks, flashes, or companion objects, must consistently appear in independently processed image stacks, with timestamps and ephemeris data aligning across multiple research teams. Artifacts, in contrast, tend to dissipate or change when processing pipelines are altered or calibration parameters are modified. Ascending this hierarchy, the next critical test is multiband confirmation. A real celestial object should register across multiple spectral filters or wavelengths, exhibiting color ratios that conform to established physical principles. Artifacts, however, frequently flicker erratically within a single spectral channel or exhibit inverted color responses under different processing conditions. Further up the ladder, geometric and dynamic hallmarks provide additional validation. Genuine companion objects, for instance, should exhibit parallel motion, maintain trackable trajectories against predicted paths, and display consistent separation distances without any sudden jumps or blurring dependent on the stacking order. The apex of this hierarchy, representing the most compelling evidence, includes deliberate maneuverability or complex structural alterations, narrowband radio emissions, or repeating geometric patterns. These characteristics are exceedingly difficult, if not impossible, for natural phenomena to convincingly replicate. Each claim advanced by researchers must ascend this structured ladder, facing progressively more stringent tests at every stage. The burden of proof intensifies proportionally with the magnitude of the claim. The scorecard remains open. Meticulously document every anomaly, demand verifiable supporting evidence, and allow the accumulated data to speak for itself. Chemically, 3I Atlas presents a significant challenge to existing cometary models. Its elevated nickel-to-iron ratio, a composition heavily weighted towards carbon dioxide, and the presence of a massive sunward-directed plume all stand out as highly unusual. However, the most critical pieces of evidence remain beyond the public's immediate view. The object's projected trajectory intersects with the recorded location of the 1977 WOW signal with a statistically calculated probability of 0.6%. Yet no independent radio detections have been reported thus far. As 3I Atlas approaches its perihelion and the subsequent observational blackout period, the available facts necessitate both patience and unwavering scientific rigor. Until the next official data release, the profound mystery persists. We are confronted with an interstellar enigma, a compilation of anomalies, and a conspicuous absence of confirmed answers. The path forward depends solely on the evidence we gather and the manner in which we subsequently interpret it.